Okay, welcome back. And so now we're going to start talking about integrals that have the form that involve this radical here, a squared plus x squared. Now also notice that, because of the commutative property, it could be x squared plus a squared. Okay, so again, make sure you are aware of that and you recognize that it could be flipped the other way, and obviously you still use this method. Okay, so now a couple things to realize. So I'm not going to go through the whole derivation that we did before, but you can go through and prove it to yourself that this works. So the domain here is going to be all real numbers, right? So there's this domain of this expression is all real numbers, right? There's no value of x or a that is going to make this negative underneath. So all real numbers are possible, okay? So that means x is on the whole number line, the real number line. Okay, now, that means that we're restricted to our substitution of either using a tangent theta or a cotangent theta, okay? So now, either one of these substitutions will work, but it's customary and standard just to use a tangent theta, okay? But again, just realize either one of these will work fine, okay? But this is the one we're going to use, okay? Now, that means that, what do we have? We have tangent theta is equal to x over a, and now we're going to assume that the interval is from negative pi over 2 to pi over 2. Okay? Because that's where tangent is going to be defined at. Okay? Why? Because why we define it this way? So we can make sure that we get theta is equal to tangent inverse of x over a. Okay? So now, with that being said, that's what we're going to use. And now, let's talk about the steps. Okay? Now, the steps that you're going to use are going to be, first of all, you're going to want to find if there's an easier way to integrate. Okay? And if there is, great, use that method. If there is not an easier way to integrate, then use the substitution that we have. So in this case, we're going to use x equal to a tangent theta, dx is equal to a secant squared theta, and then what's going to happen is this is going to be the way the radical is going to break down. Okay? So this equals this, and then you're going to distribute the power, and you're going to get a squared times tangent squared theta, and then of course, again, it's very similar to what we did last time with a squared minus x squared. Okay? So you're going to get the factor, you're going to factor out the a squared, and you get this. Now here's where the identity comes in. So there's another identity that relates tangent squared plus 1, and that's secant squared, because secant squared minus tangent squared equals 1. That's another result, another identity. So now we're going to replace this with secant squared. Now we can pull out, and we got this as a squared times secant theta quantity squared, right? So we can take the square root of both of those, and we get the absolute value of a secant theta, a times secant theta. Now we can drop the absolute value signs because secant is positive over this interval. So therefore we can drop the absolute value signs and we get a secant theta. Okay, so that's the breakdown. Then once you do that, then you're going to simplify the expression. So step 3 is simplify the expression Okay, and then once you simplify the expression, then what do? You're going to evaluate the integral using techniques that we learned in other sections. Okay? Okay, on trigonometric integrals. So we've talked about that in other videos. So we're going to integrate Okay, so we're going to integrate using techniques developed for trigonometric integrals. Okay, and then once we do that, then the last step, step 5, is to use the reference triangle. And to put things back in terms of x. Okay, so the same steps that we did before. Okay, okay, that's it. So come back and I'll be doing some examples next.